Greetings and welcome. This is Dr. BDY Sunil, Associate Professor, Mechanical Engineering Department, Institute of Aeronautical Engineering, Hyderabad. In this session, we will be learning about the work done by spring. The course outcome of this session would be calculate the forces resulting in the movement of the connected bodies by using work energy equation involving springs. The topic covered would be work done by the springs. And the topic learning outcome would be understand the principles related to the work, energy and power for solving the engineering problems. First, let us understand what the spring is and how the work done by the spring will be considered. A spring is a helical shaped equipment or helical shaped tool which will be having a characteristic of compression and expansion. And depending on the stiffness of the spring, depending on the capacity of the material of the spring, the capacity of the spring's absorption and spring elongation will be considered. That depends on the stiffness of the spring. As we have seen in several vehicles, all the vehicles, the automobiles, the wheels are not directly connected to the body, but they will be connected to the body with the absorption, shock absorption capability of the whether the spring or damper system or anything. So, this coming to the spring has the tendency to contract and expand. And keep it in mind, when the spring is contracting or changing its length or decreasing its length, then the work is done on the spring. That means we need to apply some extra force for the spring to get compressed. Whereas when the spring is expanding, let us say it is getting into expansion mode to its normal stage, then what happens? The spring does the work. That means the spring is applying some force onto the external work. So in this case, we can see that the work is done by the spring. And there are two cases where the mean normal position or normal length of the spring is considered, and compression and expansion of the spring will be limited to this normal unaffected size of the spring. So consider here a body attached to a spring as shown in figure. This is the undeformed position. This is the undeformed position of the spring here as you are seeing. So this is the spring which is fixed onto certain support. And an object is attached to this spring. An object is attached to this spring. The force of a spring is always directed to its normal position. This is the statement which is related to the spring. Let us say this is the undeformed position or the normal position of the spring, when the spring is not contracted nor expanded. Okay, let us understand this in this fashion. This is the spring and there are certain limitations to the spring, let us say. And this length L is the normal condition length of the spring. When the object is compressed or when this spring is getting compressed, that means we are doing the work onto the spring. The length, let us say it has been compressed here to this length, and that length is L1. So this would be the force of the spring which is always directed to. Now in this case what happens? The spring will try to come to its normal condition. That means it will try to come to its undeformed position. So spring will always, when it is being compressed, it will try to expand. And if at all the spring is expanded, then what happens? Again, the spring will try to come to its normal position by compressing its length. So, in each and every case, whenever we disturb the length of the spring, we can say that in any case, whenever we disturb the length of the spring, it will try to come to its normal condition or undeformed position. The magnitude of force developed in the spring is directly proportional to the displacement from the undeformed position, right? As this statement states that the force with which the spring is getting compressed or elongated, this force will be directly proportional to the length to which it gets displaced. We can say that the length to which it gets compressed or elongated. Let us say some 20 centimeter spring has been compressed toward this length of 15 centimeter. Then the force to which this 15 centimeter, that 5 centimeter distance is being compressed by the spring is utilized, it is directly proportional to the length. Then if we need to still compress the spring to, let us say, 12 centimeter, then extra force, that means more force is needed to compress the spring than this starting 5 centimeters length of the spring. So in such a way that as we are increasing the compression or elongation of the spring, we need to increase, or we need more and more force to compress or elongate the spring. So it can be stated that the force that is being applied for the disturbance that is to be created onto the spring is directly proportional to the length to which the spring gets disturbed, or the spring length changes. If F is the force developed because of the displacement of X from the undeformed position, let us say this is the force F, is the force, that is the force developed because the displacement of X. So the spring has been compressed to a distance of X from the undeformed position, then we can say that F is directly proportional to X. So from this, if we remove the proportionality symbol, then we will be obtaining F is equal to Kx, which is the proportionality constant, where K is the constant of proportionality and is called spring constant and is defined as the force required for unit deformation. Force required for unit deformation. And the units of K are the Newton per meter or kilonewton per meter. Now let any instant, if the displacement is dx, at any instant let us consider that the displacement of the spring is dx, the work done by the spring force, spring force du is given by du is equal to minus f into dx. Consider here the force into displacement. Here what we are doing, we are applying the work done equation. Work done is equal to force into displacement, and the minus symbol, the negative symbol for F is being selected here, or it is being represented here, because when the spring is compressed, the direction of the force in which the spring is having, it is opposite to the direction of the displacement, isn't it? Let us say this is the spring and we are compressing the spring in this direction. That means whatever force that we are implementing or impinging into the spring, that force will try this spring to come to its normal position, right? Come to its normal position. So we can say that the force is acting in the right side direction and the displacement of the force is happening in the left side direction. Okay, so we can say it would be a negative force for the direction in which the spring is elongating or compressing. Hence, work done in displacement of body from x1 to x2 is given by u is equal to integral x1 to x2 minus kx into dx, that is equal to minus 1 by 2 k into x2 square minus x1 square. If the displacement is from undeformed position to x, right, from undeformed position to x, then u is equal to minus 1 by 2 kx square. Okay, you need to concentrate here. when the spring is getting compressed, what is happening? The force that is induced in the spring, it is acting in the opposite direction to the displacements. That's the reason the work done is considered here as minus 1 by 2 kx square. That means the spring is, the work is done on the spring. If the deformed spring is allowed to move, what happens? When the deformed spring, already deformed spring, if it is allowed to move to its normal position, then what happens? The force is making the spring to elongate, right? So the force is acting in right side direction and the elongation is also happening in the right side direction. So both are in the same direction. So we can say that this work done is positive. That means spring is doing the work. So that can be taken as U is equal to 1 by 2 kx square. So this concludes the session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.